So I have decided to rewrite the almost OS for the DCPU that I wrote a while back. You might have seen it, probably not. It's not that popular, I guess. Um, I wrote it in a few days because I was sick and had nothing else to do. So it's kind of junky and it's still functional, but it's not as well structured as I'd like it to be. And I told some guys on ISE and they said, hey, why not make a video series out of it and explain to people how to write that sort of stuff. And so now here I am, recording my editor. I use the dev kit. I think it's decent at the very least. Some people hate it because it supports some stuff like what's it called? That one storage device. Hang on. Harold's media device, and people went mental because it might not be supported and stuff. Um, that's beside the point though. So I will start off by writing a really simple thing in assembler. I will explain everything as I go along while writing this. So hopefully you can follow my train of thought. Hopefully I can follow my train of thought. And I hope I will write decent OS and you can learn things, learn how stuff is done, or rather was done, because nowadays things work quite differently. We have MMUs and CPU rings to protect things. This is a really simple CPU, so all of this doesn't exist very much. And we should just get started. A word of advice when you write assembler code: always, always, always have the specs for the system you're writing for open. And you can use these. These are the official 1.7 specs that Notch put out. I personally like this wiki. It it's very well structured and it's easier to the eyes than ASCII text, in my opinion, at the very least. So the instruction set, that's what you want to look at the most. And one thing to note right off the bat, there is no jump instruction. There is the jump subroutine, which does what you might expect, but there is no unconditional jump instruction or conditional jump instruction instead. Instead, we have these if instructions that only perform the next instruction if their condition is met, and otherwise skip it, but just one instruction, no more, no less. And we have direct access to the PC register, the program counter. And we can use that one to set our program counter, which is basically the next instruction that will be executed. So that's how you jump on the DCPU. So to illustrate that, our program starts at address 0. Whoops, that was a typo. So if I execute this, I get an... Oh, I should save that first. And close that. Stop execution, new execution. Alright, there we go. And now it's running, no errors this time. And if we break, we can see, alright, we're there. It's always, when I step through, it always just jumps back to itself because this is at address 0. I think I can get the memory view. Alright, so this is address 0 and this is our instruction. So that's why that is happening. So we'll quit now and note that doing this is pretty messy. If I have loads of routines and I always have some literal values there, and I just change the first line, I need to patch every other one. So instead, we can use labels. So I'll call the very start of the program entry, and use entry here. And what this does is the compiler basically resolves each label to the memory address that this label's at. So this will be resolved to 0 now, and entry will sorry again, entry will just execute every time, and this should perform exactly the same. Also, if you look at the memory, this is different than before, I think. And we can just try this out again. Hang on. I'll change it to 0 again, and we'll see. So we have 7F81. Whoops. So 0 now. Run. Ah, there we go. And the reason for that is the encoding of the instructions. This this is a bit hard to see, so what I will do now is I'll add an instruction in front of this. Hang on. Let me do that and this, and this should be alright. And now what you will see is if I think should be 2. Ah, no, 1. Alright, now I run this, and you can see I'm at memory address 1 now, and it loops around. And you can see I have 2 instructions, and this one sets A to 0, this one jumps. But if now I use entry here, which should also resolve to 1, hang on, execute again. Now you can see that the 1 isn't in this instruction, but instead it's been packed into this. If a value is really small, between -1 and 30, it's packed into the instruction itself. But if it grows larger, it's appended in the next word. So what you see here is entry is potentially too big to fit in, and this compiler doesn't optimize it away. So now we use 1 more byte. Actually, 1 more word, which is 2 bytes. And that's why the instructions were different. Glad I could show that. And I think I will call it quits for now and make another video after this. See you if you tune in the next time, I think, maybe, hopefully. Well, that's it.